Welcome back to this lecture series on deep learning. In this lecture, we will briefly discuss about what is regularization, optimizer, and gradient, how it plays an important role in designing convolution neural networks. This regularization, optimizers, and gradient computations are core concepts in convolution neural networks because they directly determine how well a model learns, converges, and generalizes to unseen data. Regularization prevents convolution neural networks from overfitting by controlling model complexity, ensuring that the network learns meaningful and robust features rather than memorizing training samples. And gradient computations enable the network to understand its errors and adjust millions of parameters through backpropagation, forming the foundation of learning itself. Optimizers are efficiently use these gradients to update weights, control convergence speed, and stabilizes training. Without a clear understanding of these three concepts, namely regression, optimizer, and gradients, CNN models may train slowly, become unstable, or fail to perform reliably in real world applications, and making them essential for building effective and trustworthy or deep learning systems. We'll see one by one. First, this convolution, the computations in the convolution neural network, how it has been, we are going to, that is regularization, optimizers, and gradient, how we are going to compute in the CNNs. This presentation introduces the three fundamentals, as I've said, required for effective training convolutional neural networks, namely regularization, gradient, and optimizers. These concepts ensures that CNN models learn meaningful features, converge efficiently, and generalize well to unseen data instead of memorizing the training. So here next, why these concepts matter in convolution neural networks. And the CNN contains very large number of parameters due to multiple layer and filters, making them powerful but also prone to overfitting. That is the main drawback. Proper gradient computation allows learning from errors, optimizers control how weights are updated efficiently. And regularization techniques, what it will do, it will prevent the model from becoming too complex, ensuring stable and accurate training. And the next, training pipeline overview in CNN. During CNN training, the input image is first processed. Input image, we are going to process it through convolution, activation, and the pooling layers to extract the features. The network's output is compared with the true labels using a loss functions. Next, gradient of this loss are computed through backpropagation, and the optimizer updates the weights while regularization constraints are applied to maintain the generalization. Next, what is regularization? The regularization is a technique used to prevent convolution neural networks from overfitting the training data by adding constraints to learning process. It discourages overly complex, this regularization technique model, overly complex models, and forces the network to learn simpler, more robust patterns that perform well on unseen data. Next, overfitting means how we are going to regular. That is overfitting problems. How we are going to solve it. This is the regularization. What I've told you. This it is mainly to prevent the overfitting of the networks. And here, this overfitting occurs when a CNN performs extremely well on training but poorly on the validation. In this case, only overfitting occurs. This happens when the model memorizes training samples instead of learning general features. So we are going to apply the regularization techniques. This regularization techniques help maintain a balance between learning accuracy and also model generalization. We have various types L2, L1 regularization. L2 regularization means weight decay. We can call it as weight decay in this. So regularization adds a penalty term proportional to the square of the weight to the loss function. Square of the weight function. Here this discourages the large weights due to it results in smoother decision boundaries. It is widely used in convolution neural networks because it improves stability and generalization without eliminating important connections. So L1 regularization. So the loss function becomes we'll write it as original loss plus lambda into sum of weighted squares, and also it will prevent the weights from the growing too large, and it is mostly used in the regularization in CNNs. Next, L1 regularization means it adds to a penalty equal to the absolute values of weights. It encouraging many weights to become zero. This creates sparse models where only important connections are retained. That is unusual, that is unwanted connections are disabled. Although useful for feature selection, it is less commonly used in CNNs than the previous one, L2 regularization. Next, dropout regularization. Dropout randomly disables a fraction of neurons during training to prevent the network from relying too heavily on specific features. This forces the CNN to learn redundant and distributed representation and improving robustness. During inference, dropout is disabled and all neurons are used. So the typical dropout rates, what we are using it 0.2 to 0.5. Next, data augmentation as regularization. Data augmentation increases the size and diversity of training dataset by applying transformations such as rotation, flipping, scaling, cropping, and zooming. This helps the CNN become invariant to real world variations and reduces overfitting without modifying the network architecture. Next, early stopping. Early stopping monitors validation performance during training and stops the process when validation loss starts increasing. This prevents the CNN from training too long and overfitting the data, making it an effective and computationally efficient regularization techniques. Next, optimizer means so. This is what about the regularization. Next, the topic is the optimizer. The optimizer means optimizers are the algorithm that update the weights of a CNN based on gradient information. They determine how fast, in which direction, and the learning occurs. Choosing the right optimizer greatly influences convergence speed, training stability, and final performance. Next, the gradient descent basics. Descent is a fundamental optimization technique used in CNN to minimize the loss function. It updates the weights in the direction opposite to gradient of the loss, gradually reducing prediction error through iterative updates. Next is stochastic gradient descent, SGD. Stochastic gradient descent updates the weights using small subsets that we can call it as mini batch of training data called the mini batches. This makes training faster and introduces noise that can help escape local minima. However, the stochastic gradient descent is sensitive to learning rate and may converge slowly. There we are using SGD with momentum. The SGD with the momentum accelerates learning by adding a fraction of previous weight update to the current update. This helps the optimizer move faster in consistent directions and reduces oscillations, especially in deep convolution neural network architecture. Next one is RMS probe optimizer. RMS probe adjusts the learning rate for each parameter using a moving average squared gradient, moving average squared gradient. This prevents excessively large updates and stabilizes training, making it especially effective for deep CNNs and non-stationary objectives. Next optimizer is the Adam optimizer. Combines the advantage of momentum, the previous one, and the RMS probe by maintaining moving averages of both gradient and squared gradients. It provides fast convergence, adaptive learning rates, and stable training, making it one of the most commonly used optimization in CNN applications. Learning rate importance. Why we are going for this learning rate? The learning rate controls how much weight change during training. That means fine tuning. A very large learning rate can cause unstable training, while a very small training rate slows the convergence. Learning rate scheduling and adaptive optimizers help address these challenges. Gradient computation in CNNs. Gradient represents how sensitive the loss function is to changes in weights. In CNNs, gradients are computed for filters, biases, and fully connected layers using backpropagation. Accurate gradient computation is essential for effective learning. Next, backpropagation concept. Backpropagation is the process of propagating error backward to CNN using chain rule of calculus. Chain rule of calculus. It allows the network to assign responsibility for errors to individual parameters, enabling efficient learning across all layers. Next, gradient computations in convolution layers. This in convolution layer, gradients are computed with respect to filters. That means we are calling it as kernels and biases by reversing the convolution process. Because filters are shared across spatial locations, gradient computations become efficient and stable for large images. Next, what is the gradient issue in CNNs? CNNs may suffer from vanishing gradient points, where gradient become too small, or exploiting gradients, where they become excessively large. These issues hinder learning and are addressed using the proper initialization, normalization, that means batch normalization, and suitable optimization techniques. And the role of batch normalization. Batch normalization normalizes the activations within a mini batch, stabilizing the distribution of inputs to each layer. This improves gradient flow, allows higher learning rates, speeds up convergence, and also provides regularization effect. And combining view, that is CNN, how we are going to maintain the stability. Regularization ensures generalization, optimizes guide efficient learning, that means weight updates, and gradient computation enables learning from errors. Together, these components work in harmony to ensure stable, accurate, and scalable convolution neural network training. Coming into the summary, regularization techniques will always reduce the overfitting, and optimizers improve the convergence efficiency, and the gradient computation drives parameter updates through backpropagation. A balanced combination of these elements is essential for building robust and high performing convolution neural networks models. So I have given in my previous lecture, artificial intelligence and machine learning, the detailed discussion I have given. I'll be giving you the link if you want to learn deeply about regularization, the gradient, the techniques. You can follow the link which I have given in the description box. Hope everyone understood the concepts of these three concepts about regularization, optimizers, and gradient. The remaining things we'll discuss in the next lecture. Thank you.